David Smith here with another flipped classroom math lesson. A few tips before we start. First, remember that you can speed up or slow down the playback if that helps you follow along. Second, you can turn the captions on and read my words on the screen. Third, you can pause the video at any time to catch up with your notes or write down questions for class. This video is a review of all the differential calculus we covered in Chapter 5. So I'm going to go through all the rules, all the procedures, all the things that you need to be able to do for our unit test, but I am not going to do examples because that would make this video probably 2 or 3 hours long because the problems take a while to do. If you need specific practice with problems, please look up my other videos on this chapter on differential calculus, and you'll see there are example problems that are walked through. Okay, so let's get started. We had a bunch of rules for finding derivatives, so let's review those. First, we had our power rule. This is what allows us to take a term in a polynomial, like ax to the n power, and find its derivative. We use this notation dy dx. What we're really going to do is we're going to take the power, multiply it by the coefficient, that's the a, and then we're going to reduce the power by 1. So that is our power rule for taking a derivative. The second rule we got was the chain rule, a little bit more complicated. The chain rule is when you have one function, in this case g of x, buried inside a larger function. So this could be a polynomial inside parentheses, like something like this, 2x squared plus 1 raised to a power. So this is the inner function, 2x squared plus 1, and the outer function would be this thing squared, or x squared. So what we do is we recognize which is the inner and which is the outer, and then we take the derivative of the outer and multiply it by the derivative of the inner. That is the chain rule. Now, the product rule is a little bit different. Now, if we have a function that is really two functions times each other, this could be two polynomials, it could be two terms, whatever it is. If you have one function times another function, then the derivative of that function is just the derivative of the first times the second function, not derivative, plus the derivative of the second function times the regular function of the first. You just multiply this out and add them together, and then you have your derivative. Okay, let's look at the quotient rule. This one is the most tricky. It starts off fairly similar to the product rule, but you have to be careful. So my quotient here is one function divided by another. That's our f of x. So then f prime of x is going to be the derivative of the denominator, the derivative of the numerator, that's u prime, times the denominator minus the derivative of the denominator times the numerator. And since this is minus, the order is important. With the product rule, if you mix up the order, no big deal because it's multiplication. But division is not the same. So you have to get it right. What I do is I start with my denominator, my numerator, and then I make that my derivative, and then I follow the pattern all the way over. Finally, it's all over the square of the denominator. Okay, so these problems can get fairly tricky. If you'll remember, when we worked the problems and just found derivatives, we didn't need to spend a lot of time simplifying the resulting expression. It's only when you need to do things with that expression that you may need to simplify it. Okay, so we just looked at all the rules we used to find derivatives. Now what we're going to do is take a look at properties of those derivatives. So first, overall, when we find a derivative function, we take a function, we leave the x in there, and we find its derivative function. That function allows us to find the slope of a tangent line to the original function at any point on that function. So we find the derivative function, then we can take an x for the function, plug it into the derivative function, and it tells us the slope of the tangent line at that point. Pretty nice trick. Second thing, that slope of the tangent line is the instantaneous rate of change at that point on the function. We're doing this with functions that show curves on the graph. So it's hard to calculate the slope of a curve, but this is what we do. So we find the slope of the tangent line at a point on a curve. That is the rate of change at that point. All right, let's take a look at the first derivative. It has certain properties as they relate to the function itself. Now remember, with the first and derivative, we use those to discuss the function itself. They are directly related. They tell us things about the shape of the curve, what's happening, and so on. So, 3 states for a derivative. Is it less than 0? Does it equal 0? Is it greater than 0? And these things will tell us things about what's happening at that function for a given value of x. So remember, we're plugging some value of x into the first derivative. It spits back a number, in which case we go, oh, maybe it's a negative number, maybe it's 0, and maybe it's a positive number. So we exploit this information a lot when we're trying to figure out what's going on with graphs. So if f prime of x is negative, less than 0, the function is decreasing. If it equals 0, we have a horizontal tangent line at that point because that's the slope of the tangent line, so that's 0. So the function has what we call a turning point. And then finally, when the derivative is greater than 0, when it's positive, the function is increasing at that point. So let's take a quick look at a graph so we can figure that out. Check this out. Here's x1. The derivative would be positive because the tangent line slope is sloping upward. So I'd have a positive derivative at this point, and that reflects the fact that this line is increasing in this interval right there. x2 is right at the top of this parabola. So the function is neither increasing nor decreasing. In fact, we have a horizontal tangent line right there. So the derivative is equal to 0 at x2, and that's shown by our horizontal tangent line. Finally, at x3, the tangent line has a negative slope. It's going down like that. That tells us the function is decreasing, and guess what? The function is going down to the right, so that's decreasing. All right, let's take a look at the second derivative. And as you recall, the second derivative is just taking the derivative of the first derivative. So in a very real sense, the second derivative is the rate of change of the rate of change for a function. So here we go. Same thing we're looking at. Is the second derivative less than 0? Does it equal 0? Or is it greater than 0? But with the second derivative, it tells us different things. So check it out. When the second derivative is negative, that means the function is concave down. So it means it's got some kind of curve that's facing down. And when the second derivative is 0, the function has an inflection point. So that could be, like if this function continued on like this would be our inflection point, which is a point where it changes from concave up to concave down or vice versa. So this would be our inflection point, which I've been labeling as IP. So that's what it tells us here. And then finally, when the second derivative is positive, then we have a concave up situation. So here we have concave down, second derivative negative, second derivative 0, inflection point, and here we would have a second derivative that would be positive, and we would be concave up. Now, all this stuff ties together in graphs. So let's do one of those next. All right, let's look at a graph of a function and see what we can say about the first and second derivatives based on this graph. So here's our function. It's decreasing to a turning point there, then it's increasing to this turning point, and then it's decreasing again to that turning point. So one of the prompts you might get with something like this would be, now sketch the first derivative. So what we need to do for that is we need to mark our turning points. So there's a turning point. I'm just going to call it TP. And there's a turning point right there, TP. Now, remember what happens. The first derivative is negative when the function is decreasing. So the function is decreasing to this point. However, at the turning point, the first derivative is 0. So what's going to happen is the first derivative is going to be negative. It's below the x-axis. So the value of the first derivative is negative until that turning point where it goes to 0. Then the first derivative is going to be positive because now we're increasing. The value of the function is negative, but it can still be increasing. So decreasing, first derivative negative, increasing, first derivative positive, finally decreasing, first derivative negative again. So we have these 2 points we need to pay attention to. So I'm decreasing to here where I'm 0. So the first derivative is negative. So I'm just going to sketch it roughly like that. Now when the function is increasing, the first derivative is positive until there where it's going to go negative again. So I'm just going to go like that, and then we're going to be negative from there on out. Okay, so this would be our f prime of x. What do you think? All right, now a prompt might very well be sketch the second derivative of f of x. So now we have to remember what goes on, okay? So the second derivative is concerned with inflection points. So I have an inflection point probably right about there, and inflection points line up with the turning points of the first derivative because the first derivative is 0 at its turning point. And so the second derivative will equal 0 at that place. So the second derivative is positive when we're concave up and negative when we're concave down. So here, until this inflection point, we are concave up. So the second derivative is going to be positive until this point, and then we're in this part of the curve where it's concave down. So the second derivative is going to go from positive to negative. So it's going to look something like this. Okay? And this would be f double prime of x. Now I know these graphs were complicated, and you can be asked to sketch the first derivative from the second derivative as well, or the original function from the first derivative. Keep in mind that these graphs aren't super accurate numerically. We're not actually plugging real functions in here. So when I grade your test, I'm going to make sure that you have the right sense of it. But if your curves look a little different or your lines look a little steeper or less steep, as long as they capture the essence of what's going on, you'll be fine. We had a couple lessons on applications of differential calculus, and we did two types of problems in there. We did optimization problems, and what we did with that was, one of the problems we did was we looked at a situation where there's a company making things, and there's a cost to make the things, and there's a revenue that comes from selling the things. And of course, profit is the revenue minus the cost. And so we had a big, long problem where we had to optimize profit. There were some interesting graphs in there, and it was a good problem. We also did area problems, very common for optimization. You'll have a situation where you can't just assume a nice shape to optimize the area. They like take a side away from a box or do something that's different, where you have to use math to figure out the optimum configuration of the shape or the solid. So we did area problems with optimization as well. The second types of applications we did with differential calculus was kinematics, which is physics. And so what we did there is we took a look at the equations governing motion. And this is where differential calculus really comes together in a nice way. I think that's straightforward, perhaps easy for you to understand. And this comes from where differential calculus comes from. Newton and Leibniz were trying to analyze motion, and the existing mathematics they had couldn't do that. So they discovered how calculus can describe those situations way more accurately. So check this out. We had a displacement function. Now remember, displacement is not distance. Distance is total distance traveled over some course in time. Displacement is how far you are away from a fixed point or your starting point. So there's a little complexity there and some critical thinking in some of the problems you need to be able to answer them correctly. So displacement is where is the object? How far away is it from its starting point? Kind of like distance. Velocity is how fast is the object going? So velocity is the rate of change of displacement, of position, okay? So velocity is the derivative of the displacement function. This makes sense. Velocity is a change in position. How fast is the position changing? That's velocity. So it makes sense. It is the derivative of the displacement function. Okay, then we have acceleration. Acceleration is how fast is velocity changing? That makes sense. So acceleration is just the derivative of the velocity function. So acceleration is the rate of change of the rate of change. So velocity is changing in position. Acceleration is changing in velocity. So this stuff all hangs together. Now I know it came at the end of our unit. I think if I designed a textbook, I'd put this stuff much further up because it kind of sets the context. It helps you. I think it informs the more abstract stuff when we're just dealing with functions without reality intruding. This section is actually what we did in the very beginning of chapter 5, where we just dealt with a first derivative and we used it in a graphical way. So I'm going to remind you of that. We're not doing any specific problems, but I'm going to show you the territory that we're in. And you have all the tools to do this. You're going to be fine. So tangent lines and normal lines. So here's a function, f of x. I want you to copy that in your notes. And then I would like for you to sketch in the tangent line and the normal line. And this is just definitional. You just need to know what those lines are to draw them on there. There's no math to calculate. Okay, let's see how your sketch compares. My red line is my tangent. That crosses, it touches f of x at one point. It doesn't cross it. It just kisses that line. It comes close enough to just touch it at one exact point and then keeps going. This is a straight line, and we say that this line is tangent to L. It's tangent to f of x at the point x1, y1. Okay, so that point is called the point of tangency. Cool. Now, the normal line is perpendicular to the tangent line, also at x1, y1, but it's perpendicular. So the normal line in this case is a decreasing line that goes down that way. It's perpendicular to our tangent line. So that's the general situation with normals and tangents and curves. Now think for a minute. What did we ask you to do with this information? Okay, so you could be given f of x, some function. Okay, it could be any function. You should be able to find the derivative function. So that's using all the derivative rules that we reviewed in the beginning of this lesson, of this review lesson. So you should be able to find the derivative of a function. Second, you should be able to find the slope and the equation of lines tangent to that function at any point. So if I give you a function and I say at the point x equals 4, you should be able to find the slope of that tangent line at that point and the equation of that tangent line. So there's several steps involved in that. Most of this is algebra 2 type stuff with an IB math understanding and use of differential calculus. Finally, the third thing you might need to do is find the slope and the equation of a normal line at any point on the function. So you'll remember that these two slopes are related by the negative reciprocal. Take that slope fraction, flip it, and change the sign, and that would give you the slope of the tangent line, or of the normal line at that point. So I reproduced our graph over here, and I want to kind of orient you to those requests, those tasks that you might get back to our function. So the point of tangency is key. You're going to need the x-coordinate, which most likely you're prompted with, but you'll need to put that in the original function to get the y-coordinate. So once you have this point, this x1, y1, then you're going to use that. Once you calculate your slope of your tangent line, then you use that point and perhaps one of the two line equation forms to figure out what the equation of that line might be. And in the same way, to get the equation of the normal line, you do the same thing. You use this x1, y1 in most likely in the slope-intercept form. That's the easiest form. Plug that in with this slope, and then you'll get the equation for the normal line. So this was the kind of thing we were asked to do with these problems. So make sure you do as many of the review problems as you can as preparation for the unit test. We'll see you there. Now that you've finished the video, take a moment and jot down some notes or questions for our next class. Remember that you can also watch the video again if you want to increase your understanding. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.